Have you ever wondered how your phone can sift through thousands of your photos in like a split second? But then, some problems that seem way simpler, like finding the absolute best, most efficient route for a delivery truck, could literally stump the world's fastest supercomputers for longer than the age of the universe. Well, the secret isn't just about faster chips. It's about a hidden language of efficiency that programmers use to avoid, well, a complete computational meltdown.
So, today we're gonna decode that language. We'll start with a wild Olympic challenge that seems impossible to solve. Then we'll break down what an algorithm really is, think of it as a recipe. We'll pit two of these recipes against each other, see how we actually measure their speed, and finally, we'll crack the code on something called Big O and see why it is so unbelievably important.
All right, let's kick things off with a problem that, on the surface feels like it should be pretty easy to solve. But as you're about to see, looks can be incredibly deceiving, especially when you're talking about something on a massive, global scale.
So, picture this. It's 2018, the Winter Olympics in Pyeongchang. Organizers have a classic puzzle on their hands. The Olympic torch has to visit 80 different places all across South Korea. The question seems simple enough, right? What is the single shortest route that hits every single city just one time? You're probably thinking, come on, just have a computer check every possible route and pick the fastest one. Well, here's the thing. The number of possible routes is this, a 7 with 118 zeros after it. This number is so ridiculously huge, we don't even have a word for it. It's just astronomical.
And that right there is the heart of the problem. Even if you had a supercomputer that could check a billion routes every single second, it would still take more than 10 to the 100th power centuries to finish the job. I mean, it's impossibly long. So if just throwing raw power at it doesn't work, what does?
Well, the solution isn't about more power. It's about more intelligence. It's about the instructions you give the computer. It's not just about what you want to solve, but about crafting the perfect recipe to solve it. And this is exactly where algorithms come into play.
Algorithm is really just a fancy word for a recipe. Seriously, it's just a set of super precise step-by-step instructions. You give it some inputs, like a couple of numbers, and it follows the steps to give you the output you want, like their greatest common divisor. It's simple, it's clear, and it's effective.
But here's where it gets really interesting. For any single problem, there can be lots of different recipes to get to the exact same answer. And as we're about to see, some recipes are just way, way better than others.
So let's take a simple math problem, finding the greatest common divisor, the GCD. Our first recipe, we'll call it the tortoise, is the brute force way. It just starts checking every number, counting down one by one to see what works. But our second recipe, the hare, uses a really clever shortcut. Instead of checking every single number, it just keeps subtracting the smaller number from the bigger one. The magic here is that this totally different process gets you the same answer, but it shrinks the numbers you're dealing with way, way faster. Let's see him in action. To find the GCD of 81 and 36, our brute force method takes 28 steps. But Dijkstra's clever algorithm, it nails the same answer in just 5 steps. And that's a huge difference right off the bat.
Now watch what happens when the numbers get bigger. For 330 and 231, brute force takes almost 200 steps. Dijkstra's still only takes 5. For 1989 and 867, the gap is insane, over 800 steps versus just 8. The clever recipe isn't just a little better, it's a whole different ballgame.
Okay, so this begs the question. If some algorithms are so much better than others, how do we actually measure that? How do computer scientists talk about speed in a way that doesn't depend on what specific computer you're using?
First off, let's be clear what we're not talking about. We're not talking about whether the code is in C++ or Java, or if it's on a Mac or a PC with a brand new i7 processor. Sure, those things affect the raw speed, but they don't change the fundamental quality of the recipe itself.
So here's the key. The real measure of an algorithm's efficiency isn't about seconds or minutes. It is all about the growth rate. It's about how the number of steps in your recipe grows as the size of your problem gets bigger and bigger and bigger.
So, to describe this growth rate, computer scientists have a special, universal language. It's called Big O notation, and it's basically the secret handshake for talking about how efficient code really is.
Look, Big O isn't about timing something with a stopwatch. It's about putting algorithms into families of growth. It just looks at the worst-case scenario and asks a simple question. As your input, which we call n, gets massive, what's the general shape of the curve that describes how much work you have to do?
Okay, let's start with the Holy Grail. This is Big O of 1, or constant time.
This beautiful, flat line means your recipe takes the same amount of time whether you give it 10 items or 10 billion. It's the absolute gold standard of efficiency. Next up, something you see all the time, big O of n, or linear time. Here, the work you have to do grows in a perfect straight line right along with the size of your input. So, if you double the number of items, you basically double the amount of work. It scales pretty well. But then, we get to big O of n squared, or quadratic time. See how that line isn't straight anymore? It's curving up, and it's getting steeper, fast. This is a huge red flag. With an algorithm like this, if you double the input, the work doesn't double, it quadruples. This is where things can go off the rails really, really quickly.
So I know, these are just abstract letters and numbers, right? O of 1, O of n. Who cares? Why does any of this actually matter in the real world? Well, let me show you the payoff.
Okay, get ready because this slide is absolutely insane. Let's compare a good linear O of n algorithm with a truly terrible factorial O of n factorial algorithm, just like our Olympic torch problem. With an input of just 20 items, the good algorithm is done in a fraction of a microsecond. The bad one, it takes 77 years. Now, what if we bump the input up to just 30 items? The bad one takes 8 quadrillion years. That's older than the known universe. The difference isn't just speed, it's the difference between possible and impossible.
So, you might ask, can't we just build a faster computer to solve the problem? The answer is a hard no. Check this out. With a slow algorithm, even making your computer 1,000 times faster only lets you solve a slightly bigger problem. But with a fast algorithm, that same hardware boost lets you solve a problem that's 10 times bigger. The takeaway is simple. A smart recipe on a slow computer will crush a dumb recipe on a supercomputer every single time.
And that really is the fundamental lesson here. It's this invisible force that shapes our digital world, the thing that decides what feels instant and what is literally impossible. So the next time your Maps app finds the best route across town in a blink, you'll know it's not magic, it's the power of a really, really good recipe. So I'll leave you with this. Now that you know the secret, where do you see the ghost of Big O at work?